The physical transformation of a pure substance refers to a change in the physical state of a pure substance without altering its chemical composition. This is also known as a phase change. Examples include the solid to liquid transition, called melting, the liquid to gas transition, called vaporization, the solid to gas transition, called sublimation, and various types of solid to solid phase transitions. This chapter covers the thermodynamics underlying the spontaneous phase changes of a pure substance at specific pressures and temperatures. Let's begin by defining a phase. A phase is a form of matter that is uniform throughout in both its chemical composition and physical state. Examples of phases include solids, liquids, gases, and even various solid phases. Now, as I mentioned in the previous slide, a phase transition refers to the process of converting one phase into another at a specific temperature and pressure. These transitions occur because the system seeks to achieve the lowest possible molar Gibbs free energy under the given conditions. The molar Gibbs free energy, often referred to as the chemical potential, plays a critical role in determining phase stability. We will explore this concept in greater detail later in this chapter. Let's look at the fundamental equation for Gibbs free energy. dG equals VdP minus SdT. This equation provides us with valuable insights into how Gibbs free energy changes under different conditions. One key takeaway here is that the first partial derivative of G with respect to T at constant pressure is negative entropy. This relationship helps us understand how Gibbs free energy behaves as temperature changes and allows us to sketch its variation for a substance across a range of temperatures. Now, let's consider two important points on this plot, Tf and Tb, which represent the freezing temperature and boiling temperature respectively. As the temperature increases, we observe phase transitions. The solid melts into a liquid, and the liquid eventually vaporizes into a gas. These phase transitions are accompanied by an increase in system randomness or entropy, reflecting the greater molecular disorder in liquids and gases compared to solids. This implies that the entropy of liquid is greater than the entropy of solid. In other words, the slope dG over dt for liquid is more negative than the slope for solid. Likewise, the slope dG over dt for gas is more negative than the slope for liquid. This observation leads us to an important conclusion, that is, the entropy of a liquid is greater than the entropy of a solid. Put simply, as the system becomes more disordered, the entropy increases. This means that in terms of the Gibbs free energy plot, the slope of dG over dt for a liquid is more negative than the slope for a solid. Similarly, the entropy of a gas being even higher than that of a liquid results in the slope of dG over dt for a gas being more negative than the slope for the liquid. This trend reflects the increasing entropy and decreasing Gibbs free energy as we move from solid to liquid to gas. Now, let's turn our attention to the region below the freezing point. In this region, we can clearly observe that the Gibbs free energy of the solid phase is lower than that of the liquid phase. This explains why a substance spontaneously freezes below its freezing point. It does so to achieve the lowest possible Gibbs free energy. Next, consider the temperature range between the freezing point and boiling point. In this range, the system naturally transitions to the liquid phase. For example, a solid will spontaneously melt into a liquid, or a gas will condense into a liquid. Again, this occurs because the liquid phase has the lowest Gibbs free energy under these conditions. Finally, at temperatures above the boiling point, the substance spontaneously vaporizes into the gas phase. This phase change also ensures that the system minimizes its Gibbs free energy, maintaining thermodynamic stability. A transition temperature is the temperature at which two phases are in equilibrium, such as freezing temperature and boiling temperature, as I mentioned earlier. A phase transition that is predicted by thermodynamics to be spontaneous might occur too slowly to be significant in practice. In other words, thermodynamically unstable phases that persist because the transition is kinetically hindered are called metastable phases. For instance, diamond is a metastable but persistent phase of carbon under normal conditions. At normal temperatures and pressures, the molar Gibbs free energy of graphite is lower than that of diamond, indicating a thermodynamic tendency for diamond to convert into graphite. However, due to the presence of a significant energy barrier in the transition pathway, the diamond phase remains stable and does not transition to the graphitic phase. Phase diagram is a graphical representation that shows the regions of pressure and temperature at which various phases of a substance are thermodynamically stable. It plots pressure on the vertical axis and temperature on the horizontal axis. In this slide, I will show you what a phase diagram generally looks like, and in the next slide, I will present 3 unique phase diagrams of 3 pure substances. Phase boundaries are the lines separating the regions of phases where two phases coexist in equilibrium. Vapor pressure is the pressure of a vapor in equilibrium with the liquid phase. As temperature increases, the vapor pressure of a substance also increases. The dependence of vapor pressure on temperature is represented by the liquid-vapor phase boundary line. Similarly, sublimation vapor pressure is the vapor pressure of the solid phase, and the dependence of sublimation vapor pressure on temperature is represented by the solid vapor phase boundary line. Boiling temperature is the temperature at which the vapor pressure of a liquid is equal to the external pressure. It is represented by TB on the phase diagram. The boiling temperature at an external pressure of 1 atm is specifically called normal boiling point, and the boiling temperature at an external pressure of 1 bar is specifically called standard boiling point. The critical point on a phase diagram is where the boundary of liquid and vapor phases become indistinguishable. The temperature and pressure at the critical point are called the critical temperature and critical pressure, and they are denoted by Tc and Pc. Supercritical fluid is a single uniform phase at and above the critical point. Supercritical fluid exhibits both gas-like diffusivity and liquid-like properties. One practical application of supercritical fluids, such as supercritical carbon dioxide, is their use as an environmentally friendly, non-toxic green solvent. For example, supercritical carbon dioxide can be used to extract caffeine from coffee and tea. After the extraction, the supercritical carbon dioxide containing the caffeine can be depressurized and separated, allowing the carbon dioxide to evaporate, leaving the caffeine behind in the container. Melting or freezing temperature of a substance is the temperature at which the liquid and solid phases coexist in equilibrium. The melting temperature at an external pressure of 1 atm is specifically called normal melting point, and the melting temperature at an external pressure of 1 bar is specifically called standard melting point. Triple point is a point where three different phases coexist. Let's examine one of the three phase diagrams. This one is for carbon dioxide. Notice the positive slope of the solid-liquid phase boundary line. This indicates a direct relationship between pressure and melting temperature. In other words, as pressure increases, the melting temperature of solid carbon dioxide also increases. Now, take a look at the triple point of carbon dioxide. It occurs at 5.11 atm and 216.8 Kelvin. What's particularly interesting about this is that the pressure at the triple point is above 1 atm. This explains why at normal atmospheric pressure, solid carbon dioxide or dry ice sublimates directly into gas phase without passing through the liquid phase. Now, let's move on to the phase diagram for water. Take a look at the solid-liquid phase boundary line. Notice how it has a steep and negative slope. This steep slope means that significant changes in the melting temperature of water require extremely high pressure. The negative slope itself is particularly important. It indicates an inverse relationship between pressure and melting temperature. In simpler terms, as pressure increases, the melting or freezing temperature of solid water decreases. This behavior is tied to the fact that matter generally compresses under pressure to reduce its volume. For water, solid ice melts into liquid water when subjected to high pressure. This occurs because liquid water occupies less volume than solid ice for the same quantity. It's a unique property of water that plays a critical role in both natural and scientific phenomena. It also implies that liquid water is denser than solid ice. Another distinctive feature of water's phase diagram is the presence of multiple solid phases known as polymorphs. Now, let's examine the phase diagram for helium-4. This diagram has several unique features worth noting. First, observe the solid and gas phase boundary lines. They never intersect. This indicates that the solid and gas phases of helium-4 are never in equilibrium under any conditions. Another remarkable feature is the presence of the liquid helium-2 phase, which exhibits zero viscosity. This phase is known as the superfluid phase. Helium-4, in fact, has two distinct liquid phases, one in the superfluid state and the other in the normal liquid state. Let's take a closer look at this video. What you see here is helium-1, the normal liquid phase of helium contained in a glass vessel with an unglazed ceramic bottom featuring ultrafine porosity. The helium-1 remains securely in the container without leaking through the ceramic base. Now, observe the behavior of helium-2, the superfluid phase of helium. Unlike helium-1, helium-2 has no viscosity. As a result, it flows effortlessly through the ultrafine pores in the ceramic bottom of the container, experiencing virtually no friction during the process. This remarkable property of superfluid helium demonstrates its unique ability to traverse extremely narrow pathways with ease. On the phase diagram, the boundary between these two liquid phases forms a distinctive lambda-shaped curve referred to as the lambda line. Helium-4 also has an isotope, helium-3, which exhibits some highly unusual behavior. Notably, the entropy of liquid helium-3 is lower than that of the solid phase. This means that the liquid phase of helium-3 is more ordered than its solid phase, a rare phenomenon. Furthermore, unlike most substances, the melting of solid helium-3 is an exothermic process, not an endothermic one. Phase stability and phase transitions of a substance are determined by its molar Gibbs free energy under specific physical conditions. This molar Gibbs free energy is referred to as the chemical potential, a term given special significance in thermodynamics. Chemical potential is symbolized by the Greek letter mu. It is important to note that matter under any given set of physical conditions naturally tends to move toward a state where its chemical potential is minimized. This principle governs the stability of phases and the direction of phase transitions in a system. Furthermore, chemical potential serves as an important measure of a substance's potential to undergo chemical or physical changes. This makes it a crucial parameter in understanding and predicting the behavior of materials under varying conditions. Let's consider an important concept related to chemical potential and equilibrium. At equilibrium, the chemical potential of a substance is uniform throughout the entire sample, regardless of how many phases are present. This uniformity is a defining characteristic of equilibrium systems. Imagine a scenario where a quantity n of a substance with a chemical potential mu1 at one location is transferred to another location where the chemical potential is mu2. The infinitesimal quantity dn represents the amount of n lost at the first location and simultaneously gained at the second location. The resulting change in Gibbs free energy, dg, due to this transfer is expressed as dg equals mu2 minus mu1 times dn. This equation highlights the relationship between the differences in chemical potential and the tendency for material to transfer between locations. Always keep in mind that the chemical potential mu is equivalent to the molar Gibbs free energy. At equilibrium, dg is equal to 0, and dn cannot be 0 after the transfer, and as a result, mu2 should be equal to mu1. Keep in mind that transition temperature T transition is the temperature at which the chemical potential of the two phases are equal.